Right, can we start, Matheus?
Okay.
Yeah, so thank you all for coming. Thank you, Matheus, for giving us this talk today, for accepting the invitation to be here with us. So it's a pleasure for me to have Matheus with us. We actually studied together while I was doing my master's in Rio, in CBPF. Then Matheus continued to continue there in CBPF doing his PhD, and now he's in the International Institute of Physics in Natal, Brazil, doing his postdoc in Farinaldo Queiroz group. And today he's going to talk a bit about dark matter decay. Thank you very much, Matheus. So let's start with the talk. You have like approximately 50 minutes.
Okay. So thank you so much for having me here. It's a pleasure for me to talk to a so nice audience, so much people interested in quantum gravity and related stuff like dark matter. And I'm really glad to share with you the work I'm developing here in my postdoc in Natal at the International Institute of Physics. In the end of my presentation, I will talk a little about the institute, about our group, what are we doing here, and possible connections we can make. I think that's one of the basic ideas of the seminar talk. And basically, I'm gonna talk today about dark matter decay in the early universe. So I'm going to talk a little about the Big Bang nucleosynthesis. In the beginning, I thought in talk a lot more about Big Bang nucleosynthesis, but it's just a short time to address everything that I want. So I'm going to talk about dark matter, the Hubble tension, and some hints of how the Big Bang nucleosynthesis are important to the Hubble tension. Okay. So, okay. So this is the overview of my talk. In the part one, I will talk about particle physics, just introduction of particle physics and study of the model of cosmology. And in part two, I will talk more about the relativistic production of dark matter and dark matter decay in the universe. And endly, I'm gonna end my talk with some conclusions, perspectives, and I will present the institute, the IIP. Okay. So the particle physics and the standard model of cosmology. This is just an introduction. I have some question. Actually, in the beginning of my presentation, I wanted to put some of the phenomenological stuff, how we can obtain bounds, but in the end, I just bring some more without so much details, but just taking what is important to discuss dark matter in the context of phenomenology. All right. So I will just introduce here with the particle physics. So basically, the building blocks of the standard model are those particles. We have the quarks, up, down, charmed, strange, top, bottom. We have the leptons, electron, muon, and tau, and the respective neutrinos of the leptons. We have the bosons, the gauge bosons that the responsible for the interactions. We have the gluon responsible for the strong interaction in quantum chromodynamics. We have the photon responsible for the electromagnetic interaction, and we have the bosons W and Z that are responsible for the weak interactions. And beyond those bosons, we also have the famous Higgs boson, mainly responsible for bringing mass for some particles of the standard model, right? So we have the three families of the quarks and leptons. The first family is more lighter, is what we call the everyday matter. The other two families are more exotic, a lot more massive. And basically, this is all the building blocks that we use in order to describe the standard model within the context of quantum field theory, all right? So this is just a scheme of the interactions of the standard model. Each line here represents interaction between particles. For example, the photon interacts with the charged particles, the electron, quark, the W. The Higgs, for example, interacts with the electrons, the W, Z, and the quarks, and with itself, but it do not interact with the photon, for example, in the gluons. So the photon and the gluons are massless in the standard model. They do not interact with neutrinos. So in standard model, neutrinos are massless as well. We know that's a problem because neutrino oscillation experiments show that neutrinos have a small mass, but no null mass. It's a very small. So we need to go beyond the standard model in order to explain some questions of the neutrino masses. All right. So basically, this scheme can be represented by this Lagrangian, the dark matter, the standard model Lagrangian. We have the kinetic energy and self-interaction of the gauge bosons. We have the kinetic energy and the electroweak interactions of the fermions. We have the Higgs coupling to the gauge bosons and the Yukawa couplings with that will give mass to the quarks and to the leptons, all right? So the standard model is a very successful theory. The Higgs observation is an example of such success, but despite that, it brings some challenges in this structure. For example, we have the hierarchy problem that we can question why the Higgs mass has its value. It's much lighter than the Planck scale. So why is the Higgs mass is this value? So it's a question we can ask. We have the strong CP problem that quantum chromodynamics permits CP violating term, but we usually do not see this term. So I mean, there is a fine tuning there, or maybe we can have a mechanism like the axion mechanism to explain this problem. And axion is extremely interesting for people who work with dark matter. It's a very important candidate to dark matter. We have what we call the flavor puzzle. That's basically, we do not know how to explain the hierarchic mass of the quarks and the leptons. So I mean, we need to understand better this different mass scale of the different families. We have the matter and matter asymmetry, and the universe is dominated by matter, but the CP violation is not sufficient to explain the imbalance through baryogenesis. So we need to explain better. As I talked before, we have the neutrino masses. We need to give masses to neutrinos, for example, through the seesaw mechanism. I think that the most of you here are interested in gravity. So how we could include gravity in the standard model? How we can make a quantum gravity description of the world? It's a really interesting topic for me included. But what I really want to talk about is dark matter. I mean, we know that the dark matter, we have evidence, a lot of evidence of dark matter. We do not see directly, but we have a lot of evidence of dark matter, especially in gravitational contexts. But in the standard model, we do not have dark matter included yet. So I mean, we studied some extensions beyond the standard model that includes dark matter, and we try to see some hints, some aspects of dark matter in collider experiments, for example. So the fundamental question that we don't know how to answer is what is the nature of dark matter? I mean, we observe we have the evidence of dark matter, but we do not know precisely what dark matter is. And it's a very challenging question that I really like to work with. But why dark matter? I present a lot of interesting topics in standard model, but why particularly we should be interested in work with dark matter? I mean, I have a bias because I love general relativity, I love cosmology, so I mean, it's natural for me to try to understand dark matter. I love quantum field theory, so it's a very nice thing to work with. And I have a second bias because here at the institute, at the IIP, our group, our astroparticle group, we work a lot with dark matter in with dark matter phenomenology, in collider experiments, and in cosmology. So I have the second bias to work with dark matter because everyone here in my group work with dark matter. It's very cool to work with to be in a place where you can work with things that you really like. But despite this bias, I will try to give a scientific answer why we should consider standard model extensions with dark matter. So we have some evidence of dark matter. I can start with the galaxy rotation curves. Despite, I mean, when we observe the spiral galaxy, we observe that some kind of flat rotational curves. The rotational velocity of the galaxy remain more or less constant for large radials. Against the prediction, the classical prediction of the Keplerian decline that we expect from classical dynamics, that as we go far of the center, the rotational velocity of the galaxy will not grow, not maintain constant, but will lower and will become very, very low velocities, right? But this is not what we observe in practice. We observe a flat rotational curve, which indicates the presence of some kind of invisible mass component that gives rise to this, can explain this observation here. We have the galaxy cluster velocity dispersion. Zwick studied the Clamma cluster and revealed that the velocity of the galaxies into this cluster exceeds a lot what the visible mass can gravitationally bind. This means that if we not have another unseen component of mass, those galaxies cannot be gravitationally bind because the velocity of the galaxies are very large. So we need to have this other type of dark matter component to explain this gravitational bind cluster. I mean, it's another proof, another evidence, very strong evidence, the bullet cluster. That's basically when we analyze colliding clusters like the bullet clusters. If we look at the X-ray, for example, we can observe that a lot of the luminous matter that represented here by red, it's due to the gas into this cluster. But when we look to other galaxies or other clusters behind this colliding cluster, in the bullet cluster, for example, we can observe through gravitational lensing analysis that we have a lot more massive system, a lot more mass represented in blue. We cannot see directly this component. We just observe indirectly through the gravitational lensing effects of galaxies behind the bullet cluster. So I mean, this happens with other colliding clusters, and it's a very strong evidence that we have a dark matter, a collisionless dark matter, collisionless cold dark matter component in the universe. The structure formation is another example of dark matter. The growth and clustering of galaxies requires a non-relativistic collisional component that will be the seeds that of the structure formations. And models that just considering the baryons fail to reproduce the patterns of large-scale structures observed today. So we need this dark matter component that will be the seeds of the large-scale structures. What I really want to talk about today is the CMB, is because the anisotropy spectrum of the temperature fluctuations shows the existence of a non-luminous component, a non-baryonic component of matter. Basically, we have some kind of acoustic peaks in the CMB. This is mainly because of the photons and the photons and the baryons are tied together in the primordial plasma. And as structures start to grow, we have the dark matter to form some kind of wells, patterns, and this will attract gravitationally the baryons and photons, but the photons will exert some kind of pressure into the baryons. So we will have some kind of acoustic wave, and we can observe this effect through the anisotropies in CMB, the cosmic microwave background. And particularly the third peak of the CMB is related with the dark matter density. And when we make the fit of the CMB, we're using a lot of parameters. One of the parameters is the dark matter. We observe that we have approximately 26% of the dark matter in the universe against just 5% of baryonic matter. So it's a very important proof, evidence, we can say, of the existence of dark matter. And I also include here the Big Bang Nucleosynthesis. Despite Big Bang Nucleosynthesis not necessarily shows the existence of dark matter, but it shows, it predicts the baryonic matter density. And when we compare the results of the baryonic matter density with the total matter density inferred from CMB, for example, we can see that we have a lot. The baryonic matter density is very lower than the total and the total matter density, implying that exists another component, another non-baryonic component that composes the universe. So when we are studying any models of any different models of lambda CDM model, we can use some bounds coming from Big Bang Nucleosynthesis in order to study this new phenomenology of this new theories or these new models, alternative to lambda CDM model. All right. So as a resume of the opera, we have a lambda CDM model that describes a universe dominated by a cold dark matter component and a cosmological constant. We have baryonic matter as well, we have radiation, but we have mainly cosmological constant or dark energy and a cold dark matter component that evolves according to general relativity. And as assumptions of the lambda CDM model, we have a homogeneous and isotropic universe at large scales, so follows a 3D molemetry Robert-Walker metric. We have a non-relativistic collisionless dark matter and a dark energy modeled as cosmological constant. And we can represent the lambda CDM model by the Friedman equations. The first Friedman equation gives the Hubble parameter, that I will discuss a little later. And the second Hubble, the second Friedmann equation gives us some kind of acceleration equation. This A here is the expansion factor of the universe, right? So, I mean, as the standard model of particle physics, the standard model of cosmology, the lambda CDM model, has a lot of important predictions. I mean, the small density of fluctuations from the universe should grow into large-scale structures, and they obey a very typical power spectrum. T here is the sum of transfer function, if I'm not wrong, and N is the spectral index that is lower than 1, approximately 1, but lower than 1, and comes from inflation. And is this large-scale structure formation is confirmed by galaxy surveys, like the DESI, BOSS, Slow Digital Sky Survey, and so on. We have predictions coming from baryon acoustic oscillations, since we have a characteristic scale of the approximately this size here that should be imprinted in the distribution of the galaxies, and this size, this scale represents actually the sound horizon of recombination, and is also confirmed by by measurements in galaxy cluster like BOSS, DES, eBOSS, and so on. We have the universe expansion rate determination through type Ia supernovas, through the luminosity distance techniques, and confirmed by supernova survey. So, I mean, I can go on and further and explain a lot of predictions of lambda CDM that are correct. But what I want to explain today is in the past we have little we do not have a lot of data that we have today. We have just a small quantity of data, and we have a very big errors, statistical errors. But as the time passes, the experiments are being refined. We lower so the errors. We have now a lot of different sources of observations of the sky, and we enter in what we call precision era of cosmology. And in this precision era, some tensions are appearing when we confront different types of experiments. And a really, really important tension is the Hubble tension. Well, it basically determines the expansion rate of the universe today. H0 is the Hubble parameter. So in the beginning, we have this overlay of the late time measurements came from, for example, for Cepheids observations and type Ia supernovas, and the yearly measurements came from CMB, TabMap, BAL. But as time passes and we increase the quantity of data and we lower the statistical errors, we obtain different values of the H0 parameters, the Hubble constant. The late time measurements poses something about 73 kilometers per second per megaparsec, while the yearly measurements states that the universe expands with 67 kilometers per second per megaparsec. So this difference surpassed the 5 sigma threshold. So it's a very important, it is a very important difference. And so we have some problems here with the. It's not just a kind of error, but it's a very important error and a very important tension that is very discussed in today, in those days. So But what is the yearly time measurements? Basically, as an example, most important example, I think, is the CMB power spectrums. Is a very important example of how we can obtain the H naught from the, as I mentioned before, from the peaks, from the acoustic peaks of the CMB. So we have anisotropies characterized by a power spectrum and shows amplitude fluctuations at different angular scales. And we need to, when we use the Planck data, we can constrain, we can fit the observational, we can use the data of Planck to with the observational data with the lambda CDM model, and we need to fit using a lot of parameters, and we have 6 K parameters: the baryon density, the cold dark matter density, the amplitude of scalar fluctuation, spectral index, optical depth to reionization, and angular size of the sound horizon. I mean, we can use another set of parameters, but this is the most used parameters to obtain to fit the CMB power spectrum. We have other parameters that depends on those, as the H naught as the Hubble parameter, and we perform a likelihood analysis in order to obtain the best fit of the observed CMB spectrum. But we have some degeneracies regarding those constraints, right? Because sometimes we need to additional data like the Baum bioacoustic oscillation or Big Bang Nucleosynthesis in order to improve the constraints and break these possible degeneracies coming from the fit of CMB power spectrum, best determining the cosmological parameters. And once we determine the best fit parameters, we obtain the value of the Hubble constant. And the Planck 2018 gives us something very close to 67 kilometers per second per megaparsec. This is the yearly time measurements. Now, the late time measurements are a completely different type of measuring, a type of measurements of the H naught constant that usually is model independent because it uses the Cepheid variable stars and type Ia supernovas that are very low standard candles. There is a luminosity relation very low in the literature. So what people do, especially the shoes, the shoes collaboration, they use parallax measurements to determine the distance to nearby Cepheids and establish the period luminosity relationship. In some sense that you can obtain the distance to nearby Cepheids and use these nearby Cepheids to calibrate the distance measured for the hosting galaxies for type Ia supernova hosting galaxies that obeys the Hubble flow. So we can use the Cepheids to obtain this distance of the nearby galaxies and use this distance to calibrate the measurements of H naught using the type Ia supernovas. So it's a very complicated technique that there's a lot of uncertainties regarding these techniques, but the result from shows is very different from the result from CMB. Gives something between 73 kilometers per second per megaparsec. So it's I mean, we have other types of late time measurements using gravitational lensing, using the gravitational waves, and more recently use the James Webb Space Telescope. But the results coming from the gravitational lensing in the gravitational waves are very close to the obtained by Schulz. The James Webb Space Telescope, there's some conflict of results, some discussion ongoing on the literature. Some groups find results very similar to the yearly time measurements, to the CMB. Other groups use the James Webb Telescope and says, no, you are wrong. obtain something more proximate to the late time measurements. So there is an open discussion about what is the real results coming from James Webb Space Telescope, right? And here we have two possibilities. We have that first possibility is that the systematic errors are affecting the late time measurements, and it's giving a lot of errors, and it's leading to a high values of the Hubble parameter. And the real value is very lower than the observed. And this is one possibility. And the other possibility that we are working with is that we need to go beyond the standard model of cosmology. We have the standard model of cosmology, we have the predictions of the standard model of cosmology. However, we need to go beyond the standard model, obtain a different set of values from the fit of the CMB power spectrum that will give rise to a higher Hubble parameter, more close to the one obtained by late time measurements. So this is a real approach. This is the approach we are taking in the works that I will present here. All right. So I will enter the second part of my talk. That's the relativistic production of dark matter. And I wanted to show how the decay of dark matter in the inner of the universe can somehow alleviate the problem with the measurement of the Hubble tension, all right? So to address the Hubble tension, something must occur in the early stages of the universe during the radiation-dominated period. So we have the lambda CDM, we have three different eras: the radiation-dominated era, the matter dominated era, and the dark energy dominated era. So the CMB occurs something later, if I'm not wrong, of the matter radiation equality. And we need that something must happen in the early universe that will impact the CMB anisotropies, but at the same time will not interfere with the other predictions of the standard model. So we are going to assume some kind of dark matter, some kind of decay, cold dark matter, non-relativistic dark matter, very heavy dark matter, decay into hot dark matter, a relativistic dark matter, plus neutrino. I mean, we can consider a photon as well, but I will focus on the neutrino case. But this is the main scenario of decaying dark matter. So we are considering this scenario, and what we are supposing is that a model, the lambda CDM model, plus some kind of effective relativistic degrees of freedom. So we will have the matter radiation era. The energy density is basically dominated by radiation that's coming from the energy density of photons plus the energy density of neutrinos. Here the N is the energy density, is the number of neutrino families. That's approximately 3. It's not precisely 3 because when we take into account cosmological, the thermodynamics of cosmology, thermodynamics considerations, we observe that this is N is a little higher than 3, 3.01 if I'm not wrong. But I mean, it's approximately 3 families of neutrinos. And we will assume an extra energy in the beginning of the universe, an extra component that's basically a hot component, a relativistic component that will influences the total energy density of radiation. And the idea here is to parameterize the extra energy density as some kind of neutrino, the effect of neutrino. So we'll write this extra energy as the energy of one neutrino times the delta N effective, effective number of extra neutrinos here. It's not effect. It's not a real neutrino, but it's somehow a fractional number, and this extra radiation will mimic the effect of the neutrinos in the universe, and will increment this n effective here, and so that the energy density of coming from radiation is going to be given by this expression, very similar to the original expression without this extra energy, but now this n effective here, the number of effective relativistic degrees of freedom is not more 3, but is greater than 3. So such sense that n effective is the number of neutrino families plus this delta n effective here. But why I wanted to do that? Because when I make the plot of the Hubble parameter, sorry, the Hubble constant, 8 in terms of this n effective here, I can see from the Planck data that if we allow this n effective to vary, if we allow greater values of this n effective, we can obtain close values. We can increment as well the values of the H naught came from the CMB power spectrum, the CMB fit. So that's the idea. We wanted to increment, alleviate somehow, approximate the H naught coming from the CMB experiments, CMB measurements, from the result obtained by Schultz. So that's the main idea of this work. And we can achieve that by the decay in dark matter mechanism I showed before, because if I have a very heavy cold dark matter in the beginning of the universe, I mean, I not necessarily need to be a dark matter. It would be another type of particle, a very heavy particle. But when it decays into a more less massive component that I am assuming to be dark matter and a neutrino, I will have that this decaying dark matter will produce some kind of relativistic species at the beginning of the universe that would contribute to this extra energy density here. All right. So the dynamics of what's the dynamics of the decaying dark matter? If we assume that the dark matter, that the mother particle decay at rest, that's basically we are in the center of mass of the mother particles. So this is are the quadri momentums of the constituents of the decay, the mother particle, chi prime, the daughter particle, dark matter particle, the hot dark matter, that's chi, and the neutrino. So from energy momentum conservation, I can obtain the expressions of the energy of this new dark matter, this hot dark matter, and its momentum. And this factor here is some kind of boost factor, some kind of Lorentz factor, gamma factor, that will boost this hot dark matter. All right. So if you take into account tau here, sorry, I forgot to say, but tau here is the lifetime of the decay. All right. And if we take into account the expansion history, you can obtain this expression in terms of the time t, right? And we can obtain this boost factor here for our dark matter. But we have the cold dark matter component, and we also have this hot dark matter component. So the total energy of dark matter components is going to be given by a cold component, cold energy density plus a hot energy density. And the ratio between the hot dark matter energy density and the total dark matter, which is basically assuming that the total dark matter is approximately the cold dark matter component, we are assuming that just a small amount of the dark matter is produced by this decaying mechanism. So we can compute this ratio. We obtain this expression with F is basically the ratio between the number densities of the hot dark matter and the total dark matter component. Basically, the amount of dark matter produced by this decay. And we can use this last expression and the definition of delta N effective in order to obtain the delta N effective, the extra number of relativistic degrees of freedom in terms of the decay parameters of my table of parameters that characterize my decay, like the moderate to Doppler mass ratio, the lifetime, and the overall of hot dark matter present in the universe. So, but we need to be really careful about some of the cosmological bounds, because we are assuming the presence of a new component in the lambda CDM model, this kind of dark radiation. But as we assume this new component, we need to be careful to not because we are trying to solve the Hubble tension, but we can at the same time make the predictions of the predictions of the lambda CDM model to completely fail. So we need to take account in this. So we are going to look to structure formation if we are not going to we have that the structure formation process to occur, the majority of the dark matter must be non-relativistic at the time of matter radiation equality, because if at the matter radiation equality, the dark matter are hot, and it means relativistic, the structures could not form, or if they will form, they will not have the pattern that we observe today. So we need to be very careful to reproduce the observational data that we observe today. So the structure formation constrained the relativistic component of dark matter to be at the most 6% of the total dark matter density when structures begin to form. So we are conservatively assume that the amount of hot dark matter, the relativistic dark matter in our theory, corresponds to just 1% of the overall dark matter in order to obtain the data coming from the structure formation. The Big Bang Nucleosynthesis is a very important thing, because the dark matter decay cannot alter the density of the light element of the light nuclei abundances in the early universe. For example, we cannot see if we have a really big amount of dark matter, relativistic dark matter, and relativistic neutrinos that are produced in the early universe. We can disrupt the formation of the light element nuclei. So we need to be very careful in order to not disrupt the formation of those light nuclei, like deuterium, indium-3, indium-4, and also lithium-7, lithium-6. So, but that's the question, because the existence of this long-lived particle, its lifetime greater than 1 second that we are assuming, may induce electromagnetic injection in the primordial plasma. And this can alter the abundance of the light elements. So when we make the plot of this electromagnetic injection, and we observe the bounds come from Big Bang Nucleosynthesis together with the CMB, we observe that the lifetime of these decaying particles should be lower than 10 to the 4 seconds. And the moderate to Doppler mass ratio should be lower than 10 to the 6, in order for us to not disrupt the formation of the light nuclei. This is really, really important. It's really difficult thing to do, to obtain these new theories, these new models compatible with the cosmological observations, right? So additionally, we need that we want to dark matter to remain relativistic at the structure, at least in the matter radiation equality. So we need to take into consideration a moderate to Doppler mass ratio greater than 10 to the 4. So we limit, some sense, our our space parameters of the decay in order to obtain, in order to have this decaying dark matter particle, this decay model. So we perform a Monte Carlo simulation, use the Cambi, and we obtain H naught, that's approximately 70 kilometers per second per megaparsec. That's considered alleviate the Hubble tension. That's so we increase the value of H naught coming from the CMB to a values more closer to the Schul's observation. I mean, we do not resolve any kind the problem, but it's a possibility to alleviate the problem, all right? And this graphic here is really interesting because in the horizontal axis we have cosmology, H naught, the cosmology represented by the Hubble constant, and in the vertical axis we have parameters coming from the relativistic decay. I mean, that's just particle physics here. So these plots somehow try to solve the Hubble tension and brings together the particle physics and cosmology. So I mean, it's a very interesting thing to do. Study cosmology in the beginning of the universe with the eyes of a particle physicist. It's a very interesting. And I mean, I think I not have a lot of time anymore, so I mean, just
5 minutes.
Okay, thank you. So we exploit this relation between N effective and H naught, and in more general setting, and we construct effective theory models in order to explain this dark matter decay. We consider a mother particle as a scalar, a fermionic, and a vector one dark matter. And we compute the two-body decays, the decay rate, this two-body decay, and we obtain the effective Lagrangians for each type of decay here. And we obtain, according with the cosmological bounds that we found, we obtain the delta N effective in terms of the energy scale of my effective theory. And we plot this energy scale in terms of the masses, in terms of the mother particle mass, and in terms of the dark matter mass. So it's we studied the energy scale that described our decay scenario. And so just to finish, I'm going to give my conclusions. That particle physics and cosmology, despite seeming like two completely distinct areas of research, they have a very strong correlation, and we can use the particle physics to study the early universe and how we can use particle physics to understand the expansion history of the universe. I mean, it's a very interesting connection, very interesting correlation between particle physics and cosmology, right? So I have the paper here. We have another paper on Big Bang Nucleosynthesis, but I will not talk about today. I will just finish here presenting the IIP. So the International Institute of Physics is located here at the Federal University of Rio Grande do Norte in Natal, which is located in Brazilian Northeast. So it's very far of Rio de Janeiro, São Paulo, that a lot of people know. It's in Brazilian Northeast. It's a very central institute here in this region of Brazil because it has this international face. That is really important to, especially for people in Latin America, to have the possibility to go abroad in order to do science. Sometimes when you are in Europe or United States, you are already talking and discussing a lot of physics. Here we discuss as well, but it's interesting to people, especially in South America, to go abroad, to have this opportunity to join to great collaborations, and the International Institute of Physics has this phase, has this objective. One of its main goals behind the IIP is this international connection with important collaborations, right? So here is the Natal city, just a city with very beautiful beaches, very beautiful nature. I mean, everyone who came here will love the city. Here is a really nice, really beautiful city. It's impossible came in Natal and not like it. So this is the institute, the IIP. And as I said, it's located at the UFRN, it's the Federal University of Rio Grande do Norte. One more time, the institute is a really beautiful institute. You can check here the social media. So yeah, and we have frontier careers in here. I already say that. And the research areas that we have here in the institute are the quantum information, string theory, mathematical physics, interdisciplinary science and education, strong probability system, and in particular, what I'm working on is the astroparticles, right? And in the astroparticle group, the particle and astroparticle physics group, we work with direct detection, wind, sync, WIFTs, collider signatures, gravitational wave productions, indirect detection, CTA observations, Big Bang Nucleosynthesis, serial experiments, cosmological data. I mean, we have a lot of phases working with the dark matter stuff. And the main goal of our study is dark matter. This is our group. It's a very big group. We have Professor Farinaldo is the group leader. We have the 3 postdocs. We have 6 PhD students, 2 master students, another students from undergraduation as well. It's a, I mean, the group is becoming easy. Each time is having more and more people to work with. So those are our postdocs. I work with dark sector, non-standard cosmology, gravitational dark matter production. I have Gabriela, work with collider phenomenology. David, working with dark sector, the multi-component dark matter. We have all our students work with the dark sectors, phenomenology, gravitational waves. I would thank you, Victor, for providing this final part of the presentation. Sorry. Primordial black holes and non-standard cosmology, dark sectors, and more people. And we have a lot of events here in the institute that we are. I mean, one of the missions of the institute is disseminate and promote science in North and Northeast. So we organize numerous events here at the institute, and these are. I mean, I can make an invitation for you guys to watch our seminars. It's broadcast on YouTube, so you can just go here on to more information about. And we have other events here at the institute, the North and Northeast Brazilian Encounter of Physics. You have the IPESC School in 2026. Will happen here in Natal. So if anyone here wanted to came here, we'll be very happy to receive you here in Natal. And the IHAP of 2026 will also happen here in Natal at the institute. So, I mean, it's a very important international events will happen here in the Natal, in the IIP. If I'm not wrong, it's the first time that IHAP will be sediated here in the Latin America. So, I mean, we are very happy and very enthusiastic about this event. So, I mean, I opened the invitation for the first time in Latin America, and I opened the invitation for you guys because we have a lemma here that if you come here once, you will always come back because it's a really beautiful place. It's a really good place to do physics, and I mean, just come to Natal. I will end my presentation here. So
Thank you very much, Matheus.
thank you so much.